So I'm going to talk about some statistics I've developed for characterizing the network in a reservoir computer. My hope is if you can characterize what makes a good network in a reservoir computer, you can save a lot of trial and error in finding good parameters for a reservoir computer. These particular statistics you can compute without regard to the node type. So in a reservoir computer, we drive a fixed network of nonlinear nodes with an input signal. So I show that here. We then take a set of time series signals from these nodes. These act like a basis. We use a least squares fit to fit the node signals to some training signal, g of t right here. Well, the training involves far fewer parameters than training a neural network because it's just a least squares fit. And because it's a simple linear fit, there are no stability concerns. Because you don't need to train internal connections, a lot of constraints that apply in designing neural networks don't really apply here. The node types can actually vary by quite a bit, which means we can build reservoir computers from analog hardware. So in building a reservoir computer, we start with a nonlinear node. There aren't a lot of constraints of what this nonlinearity can be. You do have to find some way to implement this nonlinearity. We then connect the nonlinear nodes into a network. Now the network itself should not oscillate, so there is some constraint on the network and the node type. If we don't do anything to the reservoir computer, it should go to a stable fixed point. We then couple in an input signal to be analyzed, this signal S, and the vector W is a vector of coefficients that determine how that input signal couples into each of the nodes. So in training and testing a reservoir computer, we have an input signal and a training signal. We start out with a fixed network of dynamical systems, and there is feedback in that network. We take node signals, these signals R sub I, and do a least squares fit to approximate our training signal. We get a set of fit coefficients from that training. The output of the training is then that set of fit coefficients. Then for testing, we have a new input signal and a new testing signal. We drive the same network, we don't alter anything. We take the output signals from this network and we make a linear combination using those coefficients from the previous training stage. We then measure the difference between our testing signal and this linear combination of the new node signals. So to get our testing error, we know our testing signal is G prime, the linear combination of reservoir signals is H prime, so our testing error is the standard deviation of G prime minus H prime, and it's normalized by the standard deviation of G prime. So a testing error of 1 essentially would mean that we're not fitting anything. We want a small testing error. I said before we can build analog reservoir computers, and this has been done. A common type of reservoir computer is built in a laser system where we use a delay to create virtual nodes. Reservoir computers have been built using analog electronic systems or unclocked FPGAs. We don't actually need to network together these nodes. Connecting nodes is an easy way to make a high-dimensional dynamical system, but someone has actually demonstrated a reservoir computer in a tank of water. There are trade-offs versus doing a digital computer. On the one hand, because we have analog, we have the potential for low size, weight, and power, but we do have to deal with noise, and the parameters of the reservoir computer can drift. As far as speed, these reservoir computers can be trained very quickly, and the entire computer can run as fast as an individual node. So reservoir computers have been applied to some problems. They've been used for the prediction of spatial temporal systems. People have used floating point field programmable gate arrays to emulate chaotic attractors. Reservoir computers have been used in control of chaotic systems, They've been used for nonlinear system ID. There are also a few other programs. The DARPA Peach program is using photonic reservoir computers applied to signal processing problems. And there's also a DARPA Nature as Computer program, which isn't completely about reservoir computers, but part of that program involves reservoir computing. And there are many other applications in control or signal processing. So the real question for the research that we're doing in NRL is, why do these things work? And it seems like magic. You put in a signal to a complex dynamical system. You take a linear combination of the output, and bang, it solves your problem. This seems too good to be true, so why do these things work so well? Well, first thing I have to say is I don't know. But we can start trying to learn some things. So what we do know is that generalized synchronization is necessary. Otherwise, we know the reservoir signals should be diverse. There is some theory in reservoir computers, but still most people will choose parameters by trial and error. Optimizing these parameters requires simulating the full reservoir computer, and that is computationally pretty intensive. So in this talk, I'm going to look at how the network that connects these nodes affects the reservoir computer performance. So I'd like to know, what can we learn without having to simulate the full reservoir computer? And at the end, I can link the network measurements to some actual dynamical qualities in the reservoir computer. So I'm going to look at two different types of reservoir nodes. The first node is a leaky hyperbolic tangent. This has been used in a lot of studies. The first time I saw it was in a paper by Jaeger. In this case, we have a hyperbolic tangent, and we then have a linear constant out here that acts like a leak, and we set this parameter alpha as 0.35. The other type of node I'm going to use is completely arbitrary. It's an ordinary differential equation based on a polynomial, where I have linear, cubic, and quadratic terms. I just choose this form because you can approximate pretty much any function using a Taylor series like this, using a polynomial. So I can approximate a lot of different nodes depending on where I set these parameters. I pick these particular parameters. The linear parameter is 3, and the other parameters are 1 and -1. I pick these because it makes this reservoir computer stable. It doesn't oscillate and isn't unstable. So for an input signal, I'm going to use Lorentz chaotic system. I'm going to take the X signal from the Lorentz system as my input signal, so it looks like this. And for training signal, I'm going to use the Z signal from the Lorentz chaotic system. So the first thing I'm going to look at is the symmetry of the network. I'm going to start with a random adjacency matrix. All the entries in this matrix are 0 or 1. This is kind of artificial, but in this sort of matrix, we can characterize the matrix fairly easily. It's hard to know how do you characterize an adjacency matrix. So these matrices lend themselves to easy characterization. So then, to introduce some further diversity in this matrix, I'm going to flip a certain number of these edges to -1. I'm going to choose which edges to flip randomly. The fraction of edges I'm going to flip, I'm going to call epsilon sub f, and I'll flip anywhere from 10 to 50% of the edges, from +1 to -1. I can then characterize this matrix in terms of symmetry. Symmetry just means how many ways can I permute the nodes in this network without physically changing the network. So here's an example where I have a network I can permute it 3 different ways, so that's a symmetry. The number of symmetries I'm going to call xi sub s. I'm not good with Greek letters, so I think this is xi. It's a Greek letter anyway. So just some specifics. These are also in a paper, so you can look up there. I'll show publications at the end of the talk. I have 100 nodes with most 9800 non-zero edges. I'm going to vary the fraction of edges flipped from 0 to 50%. For each fraction of edges flipped, I'm going to do 20 random realizations because that can make a difference. and the spectral radius of the adjacency matrix we're going to set at 0.5. So here's effective symmetry for up to 100 edges flipped. On the left, I have the result for the polynomial ODE nodes. The x-axis is log of the number of symmetries, and the y-axis is the log of the testing error. So larger testing error means worse performance. And you see the log of the number of symmetries goes from 0 up to 10 up to 50. So that's up to 10 to the 50th symmetries. That's a pretty broad range. Roughly the testing error with the number of symmetries increases linearly. So more symmetries is worse performance. And I see a similar pattern for the leaky hyperbolic tangent nodes on the right. As the log of the number of symmetries increases, the testing error also increases. So it seems kind of obvious that more symmetries would be a bad network, but it really hasn't been tested before, so it's good to actually confirm that that's true. So if more than 100 edges are flipped, there's only one symmetry, which is identity. So then I have to pick a different measure. I can characterize by the fraction of edges flipped in this case. So here I have three kinds of nodes. The linear nodes I show in green are actually the same as my polynomial nodes, but I set the quadratic and cubic terms to 0. So for the linear nodes, as I increase the fraction of edges flipped, which is on the x-axis here, then the testing error, which is on the y-axis, stays roughly the same. Because it's a linear system, I really don't improve things by changing the network. I see for both the polynomial linear and leaky hyperbolic tangent nodes, as I flip more edges, the performance of the reservoir computer improves, the testing error decreases. I do see that the testing error does tend to saturate for the leaky hyperbolic tangent nodes when I get above 0.3 edges flipped, and for the polynomial nodes above about 0.4 edges flipped. So essentially a larger fraction of edges flipped leads to better performance. Again, more diversity in the network gives better performance. It seems obvious, but really I find in nonlinear systems, nothing is ever really obvious until you measure it. So why do we get more diversity? How can we measure this better performance? I can characterize the reservoir using covariance. I can put the reservoir time series signals into a matrix omega. So each row is the signal from, each column actually is a signal from one of the nodes. So I have m nodes and n time series points. How many orthogonal directions can I find in the matrix omega? Well, principal component analysis tells us we can find the number of orthogonal directions by taking the covariance matrix of omega. So the eigenvalues of that theta, the covariance matrix, are the orthogonal directions. So I can find the rank of that covariance matrix, which I'll call gamma. In this case, I find the rank using a MATLAB algorithm, which does have a tolerance, so it gives me a cutoff. Because of numerics, you can't say when is a eigenvalue actually 0 or singular value. So the MATLAB algorithm does have a tolerance. So looking again at my three kinds of nodes, if I look in green at the linear nodes, as I increase the fraction of edges flipped on the x-axis, the rank on the y-axis stays roughly the same, but for the polynomial and leaky hyperbolic tangent nodes, the rank increases. I do see the rank saturates for both the nonlinear node types as I increase the number of edges flipped. For the leaky hyperbolic tangent nodes, the rank saturates at 100. I have 100 nodes, and the covariance rank can't get any higher than the number of nodes, so it saturates there. For the polynomial nodes, the rank saturates at around 40. I don't really know why this is. This is something for investigation. Why does the rank saturate where it does? But this is also why the testing error stops increasing when you flip a certain fraction of edges because the rank stops increasing. Okay, let's now go beyond symmetry. Let's find some other ways to measure the node interactions and see how that affects performance of the reservoir. So I'd like to find a general way to characterize how strongly the different nodes interact. I'm going to set this up as a general distance measure between nodes. You have to go through more intermediate steps in the network to get between two nodes, well, they should have a weaker interaction. But I also want to know how strong are those intermediate connections. That should be a stronger connection. So I'm going to set this up as a general distance measure. So for two nodes, I and j, I'm going to come up with a weighted distance statistic, delta ij. It's going to be the reciprocal of the adjacency matrix elements connecting those two nodes. I'm taking absolute values because I just want the strength of the interaction. I'm taking the reciprocal because I want this distance to be smaller if the nodes are more strongly connected. I then take a natural log because these general distances can vary by quite a bit. I'm going to want to do a histogram later on of generalized distances, and there's a huge variation in the histogram. So to make it easier to take general distances, I'm taking a natural log here to compress the scale. I'm then going to find a weighted path length between nodes based on this generalized distance. And I find this by a breadth-first search. Path length between nodes in a network is well known. You just count how many intermediate steps you have to go through to get from one node to the other. In this case, each of those intermediate steps is weighted by my distance statistic, delta sub ij. Now the nice thing is I can compute this statistic without simulating the full reservoir computer. So this involves much less computation. So I'm going to consider 4 different network types here. The first network, I'm going to create a random network, and then I'm going to create a random network that is similar. And then I'm going to have a sliding scale where I can take a certain fraction of the random and the symmetric random network. So I'm adding these two together with a sliding variable that weights one or the other. I'm also going to try small world networks with different statistics. I'm going to do a scale-free network, again with variable statistics. And just because I did those networks earlier with plus or minus 1 connections, I'm going to do a network with all plus 1, minus 1, or 0 connections. The spectral radius in all these cases, I'm going to set at 0.5. So again, I'm doing the polynomial ODE nodes. The input is the Lorenz X signal, and I'm going to train on the Lorenz Z signal. So on the left, I have the covariance rank. The x-axis is the mean weighted path length on the log scale, and the y-axis is the rank. So for all 4 of these network types, as the path length gets smaller, the rank increases. This is an average over many different combinations of matrices because the path length can vary, so I have error bars on here for standard deviations. Now, for some networks, the variation in rank is bigger than others, but the trend is towards higher rank for smaller path length. For the testing error graph on the right, I see as the mean weighted path length gets smaller, the testing error also gets smaller. We see the biggest variation for that network of ones for the scale-free and for the scale-free and random networks, I have smaller variations. And the small world network shows quite a large variation of path length. So the effect of the statistic varies, but in general, mean weighted path length means a smaller testing error. But as I said, the nice thing is that I can compute this weighted path length without knowing the node type or simulating the reservoir computer. So this could be used as sort of a pre-sort to narrow down the number of adjacency matrix you needed to consider. So I can try some other kinds of networks. These are some low connectivity networks from a paper by Griffith et al. They used 5 different types of networks. These pictures show 7 nodes for illustrations. They actually used 100 nodes in their networks. So they have one network where they have a fixed in-degree network. The fixed in-degree is k is 2. Another network has an in-degree of 1 with a single connected network, that's B. And C is a network with an in-degree of 1 and a single cycle, which is then cut at an arbitrary point. D is a network that is just a single cycle, so a ring network. And E is a ring network with a cycle cut. The nodes they use are based on a differential equation version of the leaky hyperbolic tangent nodes. So I'm going to use their nodes, and they also have some hyperparameters that they found for their networks. I'm going to use their hyperparameters, but I'm going to choose for each network type, I'm going to choose a bunch of different random realizations. I think like 5,000 random realizations for each network type. So on the left is a covariance rank versus mean weighted path length. And as I see, as the mean weighted path length decreases, the covariance rank also goes up, which is what I saw with my other network types. So as the mean weighted path length decreases, I'm getting more diversity in these networks. However, if I look on the right graph at the testing error, I see initially the testing error stops, goes down, but then it goes up. For mean weighted path lengths that get less than 0, I see an increase in the testing error. So the smaller weighted path length means a smaller testing error until the path length gets less than 0. Then the error gets larger. I'd like to know why this is. So I really want to know, is there some change in the dynamics when these mean weighted path lengths start getting below 0? I looked at a lot of dynamical quantities, so I'm not going to show you what didn't work. What did work was measures of the embedding dimension for these networks. So there are a couple ways I can measure embedding dimension. False nearest neighbors is a measure of predictability. If I embed a signal in d dimensions, can I predict that signal in d plus 1 dimensions? I modified that signal for the reservoir computers. I'm not doing a delay embedding here. I'm taking, instead for my signal components in d dimensions, I'm taking individual node signals. So another type of dimension is covariance dimension. This measures geometry. I'm not assuming any determinism. This measure was first published here, and again, I had to modify it for reservoir computers in this other article. So both these statistics estimate the embedding dimension. The motion of this reservoir, it might be a 100-dimensional space if there are 100 nodes, but the actual motion can occur on a lower dimensional surface. Now these two types of dimension are measuring different things. The false nearest neighbors is predictability, the covariance is geometry. So if these two dimension measurements have similar patterns, that gives me some confidence that they're meaningful. So here for these low connectivity networks, on the left is the covariance dimension. And I see as the mean weighted path length decreases, the covariance dimension goes up. So something in dynamics means I'm getting a higher dimension as essentially I couple these nodes together more strongly. A shorter path length means that the nodes are coupled together more strongly. The false nearest neighbor dimension also increases as that mean weighted path length decreases. And I see more noticeable in the false nearest neighbor dimension, it looks like there is a change around a weighted path length of 0. So something is going on here in the dynamics that is increasing the dimension of this reservoir. When the mean weighted path length gets small, that means when the interaction between nodes starts to get big. And as I said, this higher embedding dimension can lead to a higher error. So what I've seen is that optimizing the parameters for a reservoir computer is computationally intensive, but I can use some properties of the adjacency matrix to at least cut down on the range of things you have to search. High symmetry is not good. Well, in hindsight, that makes sense. A weighted path length, a smaller weighted path length is good, unless it gets too small. I'd have to study some other types of networks to see, is that breakpoint of 0, is that always a good dividing point? So the smaller path length does mean stronger interactions between nodes, which can lead to an increase in embedding dimension. And here is just a bibliography with some related papers. And some of these papers have been submitted, so they haven't come out yet. Thank you.